Welcome to Unit 3. Congratulations on making it all the way through limits. Now we're going to take everything that you learned in Unit 2 from 2.3 specifically about the power rule and apply it to more complicated functions to find the derivatives. Previously in the product rule we saw when two functions were multiplied together. Now we're going to use the quotient rule when two functions are divided by each other. This proof is extremely similar to the proof of the product rule. It's not necessary, again, that you understand the proof or that you could reproduce it, just that you can follow along as I do it. And again, the end result is going to be what's important. So again, I use the limit formula to find the derivative. Is the limit as h goes to 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. Now I'm going to focus just in the numerator. And in the numerator, I'm going to make them have a common denominator, which is g of x times g of x plus h. And hopefully you notice that this one is missing the g of x, so I have to multiply that to the numerator and the denominator. And this one is missing the g of x plus h, and again I have to multiply that to the numerator and the denominator. So I'm going to come up with the limit as h goes to 0 of f of x plus h times g of x minus f of x times g of x plus h all over g of x times g of x plus h, and then that whole thing is divided by h. Now I have a fraction divided by a number. And in this case, or in all cases when I have a fraction divided by a number, my denominators can come together. So I want to do a quick review of that. If I have like 2/3 divided by 5, that's 2/3 divided by 5 over 1, which is 2/3 times 1/5, or 2 over 15, which is the same if I had multiplied the 3 times the 5. So that's my next step. The limit as h goes to 0, f of x plus h times g of x minus f of x times g of x plus h all over h times g of x times g of x plus h. Now I'm going to do a very similar thing to what I did in the product rule. I'm going to add and subtract the same thing so that I can use it to cancel. So in this case, I'm going to add and subtract f of x times g of x. So my limit as h goes to 0, f of x plus h times g of x minus f of x times g of x plus f of x times g of x, and then minus f of x times g of x plus h all over h times g of x plus h. And again, I can break this into the two fractions that I need. So I'm going to rewrite this on the next slide and then break it. Alright, so now that I've rewritten it, we are just going to factor out the g of x from the first two pieces and then the f of x from the second two pieces. So it'll be g of x times f of x plus h minus f of x. I'm going to make this all over h. We'll deal with the denominator in just a second. And then plus, I'm going to factor out the f of x. And I get g of x minus g of x plus h all over h. And this whole thing I'm going to put over the denominator of g of x times g of x plus h. Now this first part looks excellent. This is exactly what we want it to look like. When I take the limit of this piece, I have no trouble here. But I have some trouble here that we need to talk about. And my trouble is this is in the wrong order. This should be g of x plus h minus g of x. So what I'm going to actually do is factor out a -1. And when I factor out a -1, it falls into the correct order. At the same time, I'm also going to just distribute my limit, so I save some writing space here. So I'm factoring out that negative 1. Oops. And again, all over the limit as h goes to 0 of g of x times g of x plus h. All right, so let's see what happens here. This first piece becomes just g of x. This next piece, hopefully you notice that, is f prime minus this next piece becomes just f of x. And hopefully you notice the next one is g prime. And then now let's look at what happens to the denominator. The limit as h goes to 0 of g of x is just g of x. And then the limit as h goes to 0 of g of x plus h is also g of x. So my denominator is g of x times g of x. Which is g of x squared in the denominator. And again, this is going to be super important, and I will summarize it on the next slide. This part is the thing that's what's super important. You definitely want to have this recorded in your notebook, and I will summarize it on the next slide. And here you see that the derivative of this quotient f over g is f prime times g minus g prime times f all over g of x squared. And if I use the u's and v's, it's u prime times v minus v prime times u all over v squared. Again, I always use the u's and the v's. I think it's quite easy, and it makes it more simple for me, but if it's not doesn't feel good for you, you're welcome to do the more robust method of f's and g's. So example 3 on page 196 asks us to find y prime if y is equal to x squared plus 1 over 2x minus 3. Hopefully you see we have a function in our numerator and another function in our denominator. So here our u is in our numerator and our v is in our denominator. So just like in the product rule, the u is always first, here the u is always first. It's the top. And the v was second. Again, the v is second. It's the bottom. So my u is x squared plus 1, and my v is 2x minus 3. U prime is 2x, and v prime is 2. Now to find my quotient rule, I always multiply those two first. Again, that's why I make the circle. It helps me remember which two to do first. This becomes really important here in the quotient rule because we have that minus sign. So it's 2x times 2x minus 3 minus 2 times x squared plus 1 all over 2x minus 3 squared. Again, you don't have to FOIL this out. You don't have to simplify it. You may leave it like this, or you may choose to simplify it. If you choose to simplify it, that's fine. There's nothing wrong with that. But again, on the actual AP test, there's absolutely no need. And I would prefer if you didn't, because then you might make a mistake. But we will, just to show that it does simplify. Oops. And I don't really think I need to go much further than that. But I would prefer that you left it right here. The only time you really need to simplify is if it's a multiple choice question. The answer may not be in any form that you simplified it. It might not even be in this form. They might have factored out a 2. So you just have to be flexible and be able to, do some quick algebra in between the two. Let's try example 4 on page 197. Both part A and part B, we're going to learn a different way to do these. Maybe next unit, using something called the chain rule. But for right now, we're going to use the quotient rule. So my numerator is going to be my u. That's my function. and my denominator will be my v. So my u is 1, and my v is x squared plus x. U prime, the derivative of 1 is 0. The derivative of any constant is 0. And v prime is 2x plus 1. We do this times this. U prime times v. 0 times x squared plus x minus 1 times 2x plus 1 all over the original denominator squared. And again, on the AP test, I could leave it just like this, but I think I can simplify it because 0 times something is pretty easy, and so is 1. So it'll be negative 2x plus 1 over x squared plus x squared. And for this one, I'm going to rewrite it. E to the negative x is 1 over e to the x. So my u is my numerator and my v is my denominator. So my u is 1 and my v is e to the x. U prime is 0 and v prime is e to the x. Remember, e to the x is the only function where the derivative is itself. And then I do u prime times v. So 0 times e to the x is 0 minus e to the x over e to the x squared. So negative e to the x over e to the x squared. I could rewrite that as e to the x over negative e to the x over e to the 2x, because e to the x squared is e to the 2x. I multiply my exponents together. And again, if I'd like to simplify this, I could. I have e to the 1x in the numerator and e to the 2x in the denominator, so I can subtract them, and I'm left with e to the 1x in the denominator. So negative 1 over e to the x. I want to reiterate this because this is important. On the AP test, if this is an open response question, this answer receives the same credit as this answer. So it's always easiest to leave it unsimplified because you won't lose points for making a mistake. If it's a multiple choice question, however, you do have to simplify it because you might not see the form that you have it already as one of the multiple choice options. So in 2.3, they're reiterating the power rule for us. I'm not really sure why, but hopefully the power rule is something that's nice and handy now, and we're really good at using it. But they wanted us to see it again. I think because now they're going to use some negative exponents, even though I think we've probably already done that too. But we'll take it as a nice, easy formula that we're going to remember. So on example 5 on page 197, they want us to use the power rule for all of these. So the negative 1 comes down. Negative 1 times x to the negative 2. Negative 1 minus 1 is negative 2. So my derivative is negative 1 over x squared. Here I can rewrite this problem as u to the negative 2. And then I can use my power rule. Of course, there's nothing wrong. I could have done my u is my numerator, my v is my denominator, and then done the quotient rule. But of course, always doing the power rule is easier. So negative 2u, negative 2 minus 1 is negative 3. Same thing for this next one. I can rewrite that as 4s to the negative 5. So to take the derivative, 4 times negative 5 is negative 20. S to the negative 6, because negative 5 minus 1 is negative 6. Negative 20 over s to the 6th. Now we're talking about higher order derivatives. Sometimes we have to find the first derivative, which is what we've been doing. Other times they ask us to find the second derivative, which is just the derivative of the derivative. Then again, the third derivative, the derivative of the derivative of the derivative, and this goes on and on and on and on and on. So let's talk about some symbols here. Y prime, we call that y prime, with just one apostrophe. Y double prime has two apostrophes. I could also call it f prime or f double prime. Again, two apostrophes. If it was 3, it'd be 3 apostrophes. 4, 4 apostrophes. 5, we're gonna go to Roman numerals with the V, and then 6 VI, all the way out. And then to the n. So any number n, I can make it up there as the little exponent. And the other way to do this formula is dy over dx. This is called the Lebesgue notation. It's d squared over dx squared, or d to the n y over dx to the n. These are more like just to understand when you see them when they're asking for like f triple prime. It just means take the derivative 3 times. So here's a perfect example, example 7 on page 198. It asks us to find the second, the third, and the fourth derivative of y equals 2x cubed. So my first derivative is y prime, and the 2 times 3 comes down, 6x squared. My second derivative, the 2 comes down, 2 times 6 is 12. X, the third derivative, the 1 comes down, 1 times 12 is 12. And for the fourth derivative, the derivative of a constant is just 0. So here this function had 4 derivatives that I could find. Example 8 on page 199 asks me to find the second and the third derivative of this function 1 plus x squared times e to the x. So here I have a u and a v, and it's going to be a product rule because it's 2 functions being multiplied together. So let's see, my u prime is 2x and my v prime is e to the x. So let's find my first derivative. Y prime is 2x e to the x plus e to the x times 1 plus x squared. Now, there's nothing wrong with leaving it just like this, but finding the second derivative of this would be more complicated than if I just distributed the e to the x. So I have 2x e to the x plus e to the x plus e to the x times x squared. So now it's hopefully a little bit less complicated. And when I find my second derivative. Now this is going to take quite a bit of piecework here, because this is something separate and this is something separate. And inside each of these I have a u and a v and a u and a v. This one's nice and easy. I don't have to worry about it. Alright, so let's take it step by step. My first u is 2x and my first v is e to the x. U prime is 2 and v prime is e to the x. So now I'm still just focusing on this right here, and it's 2 e to the x plus 2x e to the x. Now let's go to the next piece here, e to the x. The derivative of e to the x is just e to the x. And now let's look at this second group of pieces that I need to do the product rule on. My u is e to the x and my v is x squared. U prime e to the x, v prime is 2x. So now we'll do the product rule again. E to the x times x squared plus 2x e to the x. Boy, there's a lot going on here. Let's see if I can simplify this at all. It looks like I have a 2x e to the x and a 2x e to the x. Well, that can make a 4x e to the x. And then I have 2 e to the x's and 1 e to the x's, so that would make 3 e to the x. So 3 to e to the x plus 4x e to the x plus e to the x squared. Now it asks me to find the third derivative. So there's my second derivative. And let's see if I can find my third derivative. Well, I already know this piece. That's known to me. And I can find this one using a u and a v. And this one's all set. So my second derivative is the derivative of 3e to the x, which is 3e to the x, plus the derivative of 4x e to the x, again a u and a v. So u is 4x, v is e to the x, u prime is 4, and v prime is e to the x. Hopefully you notice that this is extremely similar to the second derivative that we did over here. So if you just wanted to replace the 4 with the 2, and that was okay too, or you could do it all out like I did up here. So we have plus 4e to the x, I'm multiplying these two together, plus 4x e to the x, and then plus the derivative of e to the x squared, which was right here, e to the x squared plus 2x e to the x. So I'm just going to write that out a little bit neater, my y double prime. Let's see, I have this piece can go with that piece, and here can go together. So it looks like 7 e to the x plus 6x e to the x plus e to the x squared. In section 2.4, they also introduce acceleration. What's important to know about acceleration is that it's the second derivative of position. So we have position, and then velocity is the first derivative, and then acceleration is the second derivative of position. So the derivative of velocity is acceleration. Again, this is very important, so you might want to put that in your notebook at the front cover. This is kind of a really heavy unit that we're doing. We had the product rule, the quotient rule, the review of the power rule, and now acceleration. Example 9 on page 199 has quite a few parts, so we broke it into 2 slides. We might need to add a third slide as well. It says a ball is propelled vertically upward from the ground with an initial velocity of 29.4 meters per second. So that's my velocity. I'm just going to write this out without even continuing. My velocity is 29.4 meters per second. The height, s, in meters of the ball above the ground is at approximately s of t is negative 4.9 t squared. So that's my position formula. Negative 4.9 t squared plus 29.4 t, where t is the number of seconds that have elapsed from the moment the ball is released. What is the velocity at time t? I should state that this is v1, the initial velocity. It's asking for any velocity at time t, and then it wants to know when what's the velocity at 1 second. So we take the position function, s of t, negative 4.9 t squared plus 29.4 t, and we're going to take the derivative of that to find the velocity. So negative 4.9 times 2 is 9.8 t plus 29.4. And it also asked for v of 1, so I'm going to plug 1 in. Negative 9.8 times 1 plus 29.4. 19.6. And that would be meters per second. Part B asks, when will the ball reach its maximum height? So we have a ball that's going up and then it's coming down. Right here will be its maximum height. And if I'm thinking about my derivative, so this is my position function, I'm thinking about my derivative, right here, the slope of the derivative is going to be 0. So I'm looking for when is my velocity function equal to 0, because that's when the slope of the tangent line is 0. So negative 9.8 t plus 29.4. So 9.8 t equals 29.4. Or at 3 seconds. Part C asks, what is the maximum height the ball reaches? So I know that the maximum height happens at t equals 3 seconds, and I have the position function here as s of t. So I'm going to do s of 3, negative 4.9 times 3 squared plus 29.4 times 3. And I get 44.1 meters. So at 3 seconds, it has its maximum height of 44.1 meters. Part D, what is the acceleration of the ball at any time t? So I need the velocity again. Negative 9.8 t plus 29.4. And then to find the acceleration, I take the derivative of that, negative 9.8. And how long will the ball be in the air? For how long the ball will be in the air, there's two ways to answer it. I knew it took 3 seconds to climb up, so I know it has to take 3 seconds to come down, so I know it will be 6 seconds. Or I could think about when is my position function equal to 0. So when does negative 4.9 t squared plus 29.4 t equal 0? Let's factor out a t, and I get negative 4.9 t plus 29.4 equals 0. We'll set each factor equal to 0. So that's at 0 seconds right here when it starts. And then negative 4.9 t plus 29.4 equals 0. So t is going to be negative 29.4 over negative 4.9, or 6 seconds. So it lands here at 6 seconds. A couple more parts to this problem. We have part F and part G. What is the velocity upon impact with the ground, and what is the speed? So I know the velocity in EV is negative 9.8 t plus 29.4. So now I'm going to say at 6 seconds, it's negative 9.8 times 6 plus 29.4. And the velocity at time 6 is negative 29.4 meters per second. Now, it definitely should be negative because this ball is on its way down. So that should be negative. On its way up, it might be positive. Part G asks us to find the total distance traveled by the ball. So you might initially think that I should do S of 6. But that's S is the position function. So if I found the position at time 6, I'm going to be here on the ground, right back where I started. So my position would be 0. So that wasn't very helpful. But what I can find is how far up I went, and then multiply it by 2. That would be how far down I have to go. So let's find my position at time 3. So negative 4.9 times 3 squared plus 29.6 times 3. I get 44.1. So I traveled up 44.1 meters. I'd have to travel down 44.1 meters. So altogether, I would have traveled 88.2 meters.